Okay, brand new topic, complex algebra. I'm assuming that you're actually somewhat familiar with imaginary numbers. If not, you probably need to go back and review it, but just for a very, very quick review, let's say we're trying to solve a really simple quadratic, x squared plus x plus 2 equals 0, and we use the quadratic formula to solve it, so it's negative b plus or minus the square root of b squared minus 4 lots of a times c, all over 2 lots of a, which gives us, well, this is x equals, isn't it? Right off the side of the page here. So x equals that lot. So it gives us minus 1/2 plus or minus 1 minus 8 is negative 7. Square root of negative 7 over 2. And the square root of a negative number, we use the imaginary number for. So plus or minus root 7 over 2i. Remembering that I squared equals negative 1. Okay, so that's the key relationship which we're going to be using over and over again in complex numbers. So effectively we're defining I as the basic imaginary number and I squared equals negative 1. You may also see j used, and that's fine, so j squared. So you can see I or j, it means exactly the same thing. It depends on which background you're coming from. I tends to be used in the maths field. Quite often in engineering you'll see j because I is used for current, so you'll see j used. So I or j, I'll try and use them interchangeably so you get used to both of them. But the guts of it is that I squared is negative 1 or j squared is negative 1. So that's the basis of a imaginary number, is that. And this number that I've created here, this whole number here, is a complex number. Okay, and it's complex because it has a real part. Okay, negative 1/2 is a perfectly normal real number, and then it has this imaginary part here as well. Okay, so the root 7 over 2i is imaginary. So a complex number has a real part and an imaginary part. And we have two different ways of writing it. This is in Cartesian form at the moment, a real part plus an imaginary part. And the Cartesian parts we can draw on a plane, and on this plane we have the real part of the number, and we have the imaginary part of the number. Okay, so the real part I'll call A, and the imaginary part I'll call B, and here's my complex number out here, and that would be this complex number here, I'll call it Z, would be A plus IB. But I could also express that same complex number as in polar form. So in rectangular form, it's basically saying if I start at the origin, then to get to the number I have to go A in the real direction and I in the imaginary direction. But I could have given those instructions by saying starting from the middle, head off at a particular length at a particular angle. So I'll call that R for effectively a radius, but for a length. And then it's legitimate to say that Z is that length R at the angle theta. So I've got two different ways of expressing a complex number. I can express it in polar form as a length and an angle, and I can express it in Cartesian form as a real portion and an imaginary portion. And we need to be able to swap from one to the other. So just using a bit of simple trigonometry, R squared is A squared plus B squared, and the tan of the angle is B over A, and those two relationships enable us to change from polar to rectangular and back again. So for example, if Z is 3 plus 4i, then R will be R squared will be 3 squared plus 4 squared, which is just a 3, 4, 5 triangle. So R is 5, and theta is the tan inverse of B over A is 4/3, which is 0.927 in radians. Tend to work in radians in this sort of area, so get used to doing the things in radians. Not exclusively, but usually. So our complex number could also be written as a length of 5 and an angle of 0.27. Okay, so the ability to swap from Cartesian to polar is really useful, basically because there's some things that are easy to do in Cartesian forms and some things that are much easier to do in polar form.